Okay. All right. Based on direction and velocity of winds, I'm either going to have a headwind or a tailwind, and I have to kind of have a wind correction angle. I have to do something in order to fly a straight line to where I want to go. And I now can calculate how long is it going to take me from the time I take off to the time I land. That's dead reckoning. So what we're going to learn is the combination of pilotage and dead reckoning. So when we fly cross country, we're going to do both. We're going to plot a course line on a chart, and we're going to find checkpoints along the way and say, okay, well, there's the town, there's the lake, there's this, there's that, and we're flying along our route, and we're looking out the window from the pilotage standpoint, and we're also timing and writing things down from a dead reckoning standpoint to make sure that our timing is correct as we go along. So it's a combination of both pilotage and dead reckoning. That's what we're going to be focusing on today. Okay? All right. Why is this? Hang on a second. This is not what I want. That's what I want. Okay. All right. So let's talk just generally latitude and longitude. Who's never heard that term? Anybody never heard latitude and longitude? Okay. Everybody know what latitude and longitude is? Who doesn't know what latitude and longitude is? Everybody knows. Okay. Which ones of these lines are longitude? The ones that go this way or the ones that go that way? North, south. These are longitude. North pole to south pole. These are longitude. Latitude go east and west. Longitude go north and south. Okay. So longitude lines of longitude, are equal circumference, assuming the Earth was a perfect sphere, which it's not, but it's pretty close, okay? So if the Earth was a perfect sphere, every one of these circles, every one of them is the same circumference, roughly 24,000 miles or something like that. Lines of longitude dissect the Earth or divide the Earth laterally, or excuse me, lines of latitude dissect the Earth or divide the Earth laterally, and the only line of latitude that is equal to in circumference to a line of longitude is the equator, the one right in the middle. Everything else, as if that's the equator, everything north of the equator, the circle gets smaller and smaller and smaller and smaller and smaller, and south gets smaller and smaller and smaller. Make sense? Okay. So we have lines of longitude, we have lines of latitude. We can, using lines of latitude and longitude, we can locate ourselves on the globe, anywhere on the globe, through this coordinate system. So you got a coordinate system, and I could find a point right there as an example, and I could say it's a certain distance in longitude, east or west, and a certain distance in latitude, north or south. And I could find an exact point on the globe. So in order to navigate any place, we really have to have some understanding of latitude and longitude, even though you're not really going to use it too much today. We are going to use it. I'm going to show you how to find it on the chart and read it, because another thing that you have to know, especially on your written, I doubt that your practical test that they'll say anything about it, but on your written, you may very well get a question that gives you a chart and says, okay, what is the latitude and longitude of some particular airport? And so you have to find the latitude and longitude lines and count and find, what's the lat and lon of that airport. So we'll talk about that a little bit here. All right, so this is just reiterating what I just said. So we have lines of latitude and longitude. You've got north-south lines are longitude. The way I remember this, I don't know why I remember it this way, but these typically, with the exception of the equator, these are longer than these. So I remember longitude. That's just the way I remember it. You do it however you want. So longitude go north and south. Latitudes go east and west. And they're also called meridians and parallels. So the meridians go north and south. The parallels, as you can see, these are all parallel to each other, go east and west. The parallels and meridians. Okay, there's a couple of them of importance. A longitude line or a meridian line of extreme importance, and we call that the prime meridian. That prime meridian is the 0-degree meridian, okay? So we measure the degrees, longitude. If this is the prime meridian, then we go west longitude and we go east longitude, okay? So this would be 0, and we could measure west longitude all the way around to 180 degrees, and we measure east longitude all the way around to 180 degrees. Make sense? Okay, this line of longitude right here goes right through England. This is Zulu time. This is UTC, Universal Coordinated Time Zone. So right here, everybody heard Zulu time in aviation? You've heard that term before, right? So it is currently 9:10 local. So what's the Zulu time right now? 3:10. 3:10. So in England right now, it's 3:10 in the afternoon, or 15:10 on the 24-hour clock, okay? So this prime meridian is from where we are 6 hours ahead of us. We are 6 hours behind it as the globe spins, okay? We use Zulu time in aviation what to me seems like a logical reason. Maybe it doesn't to you yet, but I'll explain it to you. If you're flying an airplane, especially east and west through different time zones, your watch isn't correct for local time often, right? But if you always use as a reference point of Zulu time, your time Zulu never changes, right? Because that's where it starts. So that's why we use Zulu time in aviation, and we just have to then know how many hours behind. In this case, if we're flying in the United States, we're always behind the Zulu time. How many hours behind Zulu are we? And it's either -5 or -6, depending on whether we're daylight savings or standard time. Okay? All right. A couple of the other lines of parallels or latitudes that are important. Obviously, the equator. Then you have you've heard of these: Tropic of Cancer, Tropic of Capricorn. Those are lines of parallels. Okay, and then the Arctic Circle way up here. All right, so we fall typically in the United States somewhere in the 20 to 50 latitude range, and then our longitude will be whatever it is east. Right here we're somewhere around 100, close to 100 east longitude or west longitude. Okay, how it's measured, pretty simple. Go from the center of the globe, center of the Earth, and you just measure angularly. So if you're measuring degrees latitude, if this is the equator right here, and you're at the equator and you measure how many degrees north, that would be 40 degrees north latitude, okay? If you're measuring longitude, if this is the prime meridian, and you're measuring easterly, 50 degrees from here, that would be 50 degrees east longitude. So that point would be 50 degrees east longitude, 40 degrees north latitude. Okay? I don't see any eyes rolling back in the head, so everybody's pretty simple, right? Okay. All right. Latitude and longitude are divided into degrees, minutes, and seconds. This one can be confusing for some people. So there's 360 degrees in a circle, right? Every degree can be divided into 60 minutes, and every minute can be divided into 60 seconds. And by using this subdivision of degrees, minutes, and seconds, we could find, this point that's, right here, not exactly on a specific degree. You can, get a little tighter on your measurement. All right, while I have this up here, let me talk about a statute mile and a nautical mile. What's a statute mile? Because we use statute miles, at least in the United States, you use kilometers, right? And what do you use in Germany? Kilometers? Kilometers, yeah. So we use statute miles here in the United States. What's a statute mile? What's the length? How many feet? 5,280. 5,280 feet. That's a statute mile. But we typically use nautical miles in aviation, and we use nautical miles in boating and stuff. What's the length of a nautical mile? And why is there a difference? A nautical mile is 1 minute. A nautical mile is the length of 1 minute in longitude. That's a nautical mile. Okay? So if you were to divide, this 360-degree circle into its degrees, minutes, and seconds, 1 minute of longitude equals 1 nautical mile. And it happens to be about 6,080 feet, or 6,000, yeah, somewhere around 6,080 feet, 6,076 feet, something like that. So basically you're taking 24,000 miles and whatever that is and dividing it up, and you end up with a nautical mile. So the advantage of using a nautical mile, and the reason that we use nautical miles in navigation should be pretty obvious. We're navigating by latitude and longitude, and when you subdivide that down and you get to something, some divisible length that you can work with, a nautical mile is what we use. Okay, so that's where nautical mile comes from. Okay, and I'll show you the nautical mile on the chart here in just a second. Actually, why don't we go ahead and open up our charts real quick. You don't have to open it all the way because that's going to make a mess, but do you have a chart? Let me borrow yours real quick. Let me show you something before you do. Hold it like this. Don't open it yet. Hold it like this. Okay? And when you see it like this, you see San Antonio, okay? You see the effective dates, and with the exception of this one, all of your charts are expired. I guarantee this one's not expired. But they look like this. These are all of the charts that are published in the United States. You have the San Antonio sectional in your hand. It's hashed out, okay? And you see those little purple squares all over the place. Everywhere you see a little purple square, there exists, if you remember back to the airspace class, there exists a Bravo airport. So everywhere there's a little magenta square is a Bravo airport, and that is where another type of chart called a TAC chart, terminal area chart, is published. So it is like a sectional, but it's blown up twice as big, so you have bigger detail. Okay. All right, now across the top, right at the top of that, on the both sides you see north and south. One of them is right side up and one of them is upside down. Okay? There's two sides to this chart. There's a north half. So if you take the chart and you drew a line in the middle, half of this chart is printed on one side and half is printed on the other side. So if you want to see the south side, which is upside down, right? Here's what you want to do. Just open your chart kind of like this, turn it so that south reads correctly, and open it that way. And now you're looking at the south side of the chart. And I want you to open up to the south side of the chart and just have it kind of folded like this so it's not so huge, and you see San Antonio right there. All right. I'm going to pull up something here so that I can All right. Let me get the same chart out that you guys have here. Oh, I'm on it. All right, I'm going to get San Antonio. Okay, so this is the San Antonio chart that you guys are looking at, except that you can only see half of it. You're looking at this half down here right now, so I'll zoom into this half down here. So there's San Antonio right there. Everybody see that? Are you freezing right there? Okay, right in front of that. All right, if you look, when you see San Antonio right here, you'll see this line right here. You see that line with the tick marks on it? That's a line of longitude. That happens to be the 98 degrees, that's 98 degrees west longitude. Over here is 97 degrees west longitude. So there's 97 degrees, 30 minutes. 98 degrees, 30 minutes. 99 degrees, 30 minutes. 100 degrees, 30 minutes. Okay? So there are 60 minutes in 1 degree. So between here, 97 and 98, that's 1 degree, and each little tick mark is 1 minute. 1, 2, 3, 4. There's 30 minutes. 31, 32, 33, 40, 50, 60 minutes. That's the next degree. See that? If we go north, this is the 29 degree north latitude, because we're north of the equator. we know we don't have to put west and north on these because we know that we are west of the prime meridian, and we know that we are north of the equator, right? So we know that here in the United States, every longitude line is west, and every latitude line is north. So we don't have to print it on the chart. All right, so here's a line of latitude right here. This is 29 degrees north latitude. 29 degrees, 1 minute, 2 minutes, 3 minutes, 4, 5, 6, 7, 8, 9, 10 minutes, 20 minutes, 30 minutes. So this is 29 degrees, 30 minutes north, okay? Every one of, and this only applies on longitude, it doesn't apply on latitude. Look at the spacing between these little 1 minute marks. It's hard to tell right here. They look kind of the same, but they're not. The spacing on these is larger than the spacing on these because remember, these circles of latitude are getting smaller the farther we go up. But these tick marks, these 1 minutes of longitude are the same distance no matter where you look. So every minute is a nautical mile. That's 1 nautical mile, 2 nautical miles. From here to here is 30 nautical miles. All right? So every minute of longitude is 1 nautical mile. So when you're finding latitude and longitude on the chart, it's printed all over the place. You would have to count the tick marks. So if we wanted to look and see where Yoakum is located, latitude and longitude, from a longitude standpoint, here's 90 degrees west. So this is about 90 degrees, where's 10? Here's 10. So about 90 degrees, 9 minutes west, something like that. 90 degrees, 9 minutes west, longitude. 29 degrees, there's 30, so 29, 28, 27, 26, well there's 20, so about 19. 29 degrees, 19 minutes north, latitude. See how I did that? You're just finding yourself on that grid pattern. Okay. All right. Any questions on latitude and longitude? Because I want to move off of that. Okay, good. Let's get to the navigation side of things. All right. Did everyone get a did everyone grab one of these? Did everyone get one of these sheets? Okay. Who needs one? Okay, this is a navigation log. It's a navigation log sheet. This is an example of, it's kind of cut off up there, but it's an example of what we use when we're planning our cross countries. These come in a lot of different flavors. You may have seen different formats for navigation logs, and that's fine. They all kind of do the same thing, all right? They're designed to plan your flight, your VFR flight. And everything we're doing today is VFR. IFR nav logs look completely different than VFR nav logs. We don't necessarily need the same kind of, we don't need to be looking at the same things necessarily. Some of the things are the same, but other things are different. But from a VFR standpoint, they're generally going to incorporate these items on a VFR nav log. So the first thing we're going to do before we start planning this theoretic cross country is I'm going to talk about all of these columns. Let me just bring this down so you can see it there. I'm going to talk about all these columns and what they mean, all right, right off the bat first. So I'm going to start over here. I'm going to go this way. All right, checkpoints, fixes. What are we talking about with checkpoints, fixes? Remember I said when we're doing dead reckoning, we're timing, right? We want to know how long it's going to take us to get from here to here to here to here. So checkpoints are things that we visually identify and say, okay, I'm here and here's the time. Now I get to here, here's the time, get to here, here's the time. But there's really two kinds of checkpoints that we can talk about. We can talk about those timing checkpoints like this. So we use for timing purposes to calculate time, speed, and distance. Remember last week on the E6B, we did time, speed, distance problems. We were doing that to get us ready for today's class to be able to do these time, speed, distance problems while we're on a cross country or while we're planning a cross country. But a second type of checkpoint is what I'm going to call a situational or position checkpoint. And what I mean by that is they keep us on course, but we're not really timing, okay? So if I'm flying to Fredericksburg, as an example, well, Canyon Lake is a good visual. I mean, it's hard to miss, right? But it's a big body of water. Where would I start or stop a timer? The best thing to use Canyon Lake for in that case is a situational or a positional type checkpoint. In other words, I better see it over here. If I see it over here, I'm not going the right way. It needs to be over here. So does that make sense? And San Antonio, the town, needs to be over here, and Austin better be over there, or I'm going the wrong way, okay? So those are kind of obvious, but you can still use them as checkpoints, but they don't necessarily go on this sheet. They're just mental, or they're when you plan your line, when you plot your course on the chart, you see, okay, well, as I'm flying along, this town's over here, that lake's over there. So it's not something you need to necessarily jot down on here because it's presented on your chart. Okay, what makes a good checkpoint? What makes a good timing checkpoint? Needs to be easily identifiable, okay? So what do you think about towers? Think those would be good checkpoints? Towers like cell phone towers? Think those make good checkpoints, radio towers?
Most of them are really similar, so I don't know if they're in a distinctive area. Yeah, they might be good, but if they're in like rural areas towards like fields and stuff, you might mistake one for another and then go the wrong way.
Okay. What if you're at 10,000 feet?
No.
You ain't gonna see them. So towers typically aren't gonna make good checkpoints, mainly because you can't see them. So if you're flying at an altitude whereby you're using cell phone towers, you're too low. First of all, don't be doing a cross country that low, okay? So towers, generally speaking, don't make good checkpoints. What about roads, towns, rivers? So roads could make a good checkpoint. Let's say you got a road right here and you're flying in this direction. All right, well, when you cross that road, it's certainly easy to cross that road and say, okay, I'm on top of it right now so I can start or stop my timer. Correct? Okay, that's true, except how do you know you're crossing it here and not here or not here? Right? So roads make good checkpoints, but you need some further corroborating information. Maybe you need a town over here, or you need a railroad track that comes through here, or you need a crossing road. You need something other than just a straight road. Does that make sense? Okay. But they make good checkpoints as long as you have other things corroborating what you're seeing. All right, let's move to this next column, VOR, the VOR column. So VOR, identification and frequency. If you're going to use a VOR, and we're not going to do that today for purposes of this, but if you were going to use a VOR, this is a VOR on a chart right here, and let's say you were going to plot a checkpoint or something off of a radial, then you could use the identification for that VOR, that'd be the frequency, or the ident would be the three-letter identifier, or the frequency, and you could put the radial over here as a checkpoint fix. Okay, we're not going to do that today. You may do that when you're in your actual cross-country training. I do it with my students in the actual cross-country training when we start talking about VORs. But for today's purposes, we're not going to be using that. But that's what that's for. All right, and the next column is our course or our route. All right, this would be applicable if I was using a VOR. I might say, you know, radial, the 331 radial or something. That would be a good place to put that. Otherwise, what I typically do here is I'll put a D with an arrow through it to say direct. This is just a direct route. I'm going from here to here on a straight line. Okay. All right, next column is the altitude column. All right, this one we have to think about a little bit. What altitude are we going to fly at? There's a number of things that come into play when you want to determine what altitude we're going to fly at. One big one is weather. Okay, let's say you want to fly at 8,000 feet, but the ceiling's at 5,000 feet. Guess what you're not flying at? 8,000 feet, right? So the weather is going to be a determining factor on what altitude you fly at. Not only the ceiling, but the winds. Right? The winds up there are going to be a determining factor. So let's say there's no ceiling whatsoever. There's no clouds. You can fly as high as you want. Okay? And let's say that you check the weather, you check the winds, which we'll show you how to do that. You check the winds, and let's say at 9,000 feet, 9,500 feet, you plan to fly at that, but you had a headwind of 30 knots at 9,500 feet. But if you drop down to 5,500 feet, you got a tailwind of 10 knots. Where are you going to fly? You're going to fly at 5,500 feet, right? So you have to look at a lot of things when it comes to choosing your altitude. Weather's a big one. Airspace along the route. Well, if you're going to be flying, let's say specifically through like a Bravo airspace, and you can't get above it, right? Then, you know, or you could get above it, you know, airspace along the route is something you want to look at. Terrain elevation. This isn't such a big deal flying in the part of country where we fly. I mean, you have the hill country, but as long as you're above, you know, 1,500, 2,000 feet, you're not going to hit anything, okay? So we don't worry about that too much around this part of the country, but there are parts out west where you need to worry about it. And then the last one to think about is the VFR cruising altitudes. All right, so VFR cruising altitudes only apply, and I see a lot of confusion with students about this, when you are 3,000 feet or higher above the ground. Above the ground, not what your altimeter says, but above the ground, okay? So if you are planning your flight and you plan to be above 3,000 feet AGL, then we have to use VFR cruising altitudes, which say that if we are generally easterly, so from 0 to 179, anywhere in this half, then we're going to go at an odd 1,000 plus 500 feet. So 3,500, 55, 75, 95, 11.5, 13.5, okay? So if we're going in this direction, we're going to fly at an odd 1,000 plus 500 feet. If we're going the opposite direction, it's an even 1,000 plus 500 feet, okay? So however you want to remember that. The way I remember it is, I think of Washington, D.C. There's a lot of odd people there. That's what I think of. I think of east odd, west even, but however you want to remember that. But it only applies if you're flying above 3,000 feet AGL. So if you're flying out here in the practice area and you're flying at an indicated altitude of 3,000 feet, do you need to worry about this? No, because you're only 2,500 feet above the ground, rough generally speaking, so you don't have to worry about it. So you need to take into account what's the ground elevation, then add 3,000 to that. That's when it applies. Okay. Next column is the wind column, and there's three things here in the wind column. We've got direction, velocity, and temperature that we'll fill out in the wind column. This information we're going to get from the Weather Service Station. We're going to get it from what? We talked about it, huh? ATIS. Not ATIS. We won't get it at ATIS. What will we get from ATIS?
Airport.
We'll get surface information. What do we want here? We want the direction, velocity, and temperature at that altitude. That's what we want. We don't want it at the surface. We want it at that altitude. Okay. All right, so where do we get that from? We talked about it in the weather products class a few weeks ago. You go to 1-800-WX-BRIEF, okay, and you do your flight plan. You get a standard briefing, and guess what one of the things that comes out on that standard briefing is going to be? It's going to be the direction, velocity, and temperature of the wind at the altitude that you've said I want to fly at. That's where you're going to get it from. So you're going to get it from a winds aloft forecast, all right? And this is a very important box right here. This is a very important box because everything this way, from a planning standpoint, is determined based on what you put right here. And guess what this is that you put right here? Of the products, there's two types of products that we can get, weather-related products. What did I say? Two big types of products. One is current and one is forecast. Which one is this? Forecast. Okay, so what does that mean that it is? Wrong. So everything this way is wrong. It's really close, but it's probably wrong. I don't want to say wrong. I want to say probably wrong. Okay. So what I'm telling you right now is as we start filling out this side of the chart, we don't need to split gnat's hairs. I think I mentioned this last week. If you come up with 155 knots for a speed, which is based on this stuff here, true airspeed, if you come up with 155, you come up with 154, you come up with 156, you're all correct. You're close enough. If you come up with, 91 degrees, 92 degrees, 93 degrees, perfect, right? It's close enough. because it's all predicated on something here that's not exactly correct. All right? So this is a planning thing. We're going to plan this. This is the strategy. Then we're going to go fly and get punched in the face, and we correct it as we go. Okay? All right. So when we're calculating, when we're doing this, when we get this, we're going to get it from, typically we'll get it from 800wxbrief.com, but you could go to aviationweather.gov, or you get it off of 4Flight. There's lots of places you could get it. It's all pulled from the same place, from the National Weather Service. Okay. All right, the next column is your airspeed column. And we've got two kinds of the 4 airspeeds that I talk about in this class, indicated, calibrated, true, and ground speed. We have 3 of them on this chart. We have calibrated airspeed, which is the one we're going to start with up at the top here. We have true airspeed, which is what we're going to calculate. And if you recall last week when we used the backside of the E6B, remember when we were using the backside of this, what 2 pieces of information did we get? We got the wind correction angle and the ground speed. All right, so we'll end up, when we're calculating this column, which I'll get to next, it's going to give us the ground speed over here. Okay. All right, now we're going to enter into 4 columns that are all heading related columns. Okay, we're going to start with a true course, and we're going to work our way over and end up with a compass heading. That's essentially what we want to end up getting to so that we can get where we want to go. All right. So true course, what's a true course? True course is the direction of flight measured in degrees from true north. So if the North Pole is up here on the globe, North Pole is up here and I want to fly this way, my true course is the number of degrees from true north to the direction I want to go. Whatever that number of degrees is, that's my true course. If I'm going over here, that's my true course. So whatever that is, we call it a true course because it's measured from true north. So in other words, one of those lines of longitude which goes north and south. So if you were to measure the number of degrees from north and south to whatever your course line is, that would be your true course. So you could take any of those lines of longitude on the chart and measure the degrees to your line that we end up drawing on there, and that would be your true course. Okay. Once we have true course, we have to figure out what the wind correction angle would be. So if I'm flying in this direction, if that's my true course, I want to go this way, I've measured it from true north, but the wind is blowing like this, okay? I can point my nose this way, but I end up drifting this way because the wind pushes me. So I have to have some number of degrees that I angle the nose, wind correction angle, so that I don't get pushed and I continue flying. My nose is pointed that way, but I'm flying this way. And this is my wind correction angle to keep me flying that way. We're going to calculate the wind correction angle. Once we do that, we end up with a true heading. Okay? With true heading, we have to adjust it for variation. Variation is the difference between the North Pole and the magnetic north, right? I've talked about this before. Santa Claus lives where? At the North Pole, where all the lines of longitude comes together, right? That's where Santa Claus lives, right? But if you wanted to walk, drive, fly, sail to the North Pole, what instrument would you carry along with you to get there? There's one instrument that we would use to go there. It's called a compass. It's a magnetic compass, and it points north, right? Except it doesn't point to true north. It points to magnetic north. So you would not end up at Santa Claus's house. You'd end up in northwestern Canada someplace, or somewhere way up there, because the North Pole and the true north don't align. Okay. So what happens is you have true north here, you have magnetic north somewhere over here, and by the way, geographically, this never changes, right? That's always right there. This moves around. This bounces around. The magnetic North Pole is never in the same place.
And fun fact, around,
fun fact.
Either 600,000 or 60,000 years, North Pole and South Pole flip.
That's true. They do. That's a fun fact. All right, so if I am here in where I grew up and I want to go there and I use a compass, it's going to take me there, and therefore, this angular difference is variation. And so I have to apply that angular difference in my planning if I want to fly something on a compass to get where I want to go. That's variation, okay? This is an example of the lines of variation across, as it relates kind of to the United States. Now this, I've had this slide for a long time. This is not current anymore because the magnetic north has changed, so this is constantly changing. But at the time when this was done, this was the variation. So this zero line of variation, that's called the agonic line. That's called the agonic line. So that's the line where true north and magnetic north actually line up. So if you happen to be flying on that line, you can line up your compass and it all works. There is no variation. They happen to line up, okay? But anything east or west of that, you have some variation that you have to contend with and do something about with respect to your planning. All right. So, what does that look like? This is the easiest one to deal with. If you still have your charts out, if you don't, that's okay. You can look at it right up here. If you still have your charts out, well, this is Chicago. Let me go to the sectional wherever you guys where we're at here. Okay, so here's the San Antonio sectional. You can see San Antonio in the upper left there. All right, so if you look, you see this magenta dashed line right here? And then you come east a little ways and you'll find another magenta dashed line. And then if you go east from there, it's off this chart, there would be another magenta dashed line. Come this way, there'd be another one. Those are lines of variation. So when you look at your chart, if you see just to the east of San Antonio, you'll see a magenta dashed line. Down at the bottom, it says 4 degrees east. Okay, it says 4 degrees east. And if you went a little further, it would say 4 degrees, 30 minutes east. And you went a little further, it would say 5 degrees east. 5 degrees, 30 minutes east. 6 degrees. And if you went the other way, 3.5 degrees east. 3 degrees, 2.5, 2, 1.5, 1, 30 minutes, and then 0. 0 would be the agonic line. So the agonic line is not far from us. We're not too far off. The agonic line's over here someplace. Okay? So what do we do with this information? Well, it's really simple. You remember east is least, west is best. It also, if you look at your chart, if you look at your nav log, it says it at the top of the box there, minus E plus W. So if you're flying anywhere in this area, which we are, the line of variation that's closest to where you're flying, so in this case right here, this 4 degrees east, what would we do? We would subtract 4 degrees. East is least, okay? So variation, accounting for variation is really simple when it comes to flight planning because all you have to do is look at the chart and find the variation line and either subtract it or add it, okay? Okay. All right. Let's move to the next box. All right, so we found so we got true course, we calculated wind correction, that gave us true heading. We find the variation, we add it or subtract it, that gives us magnetic heading. Now we have to account for deviation. A lot of steps we got to go through. You can't just draw a line on the chart and say, okay, well, I'm going that way. If you're using a compass to go that way, you've got to go through you got to account for the wind, you've got to account for magnetic variation, you've got to account for deviation, and you finally end up with a compass heading. So what is deviation? Deviation is pretty simple to understand. If you take a compass, it's a magnetic device. If you take a compass that's pointing north, and then I were to move that compass over next to some metal object, what would that compass do? It would deviate. So when you take a compass that's out in the parking lot, points directly at north, and then you go get in your airplane and you put it up on top of the instrument panel, what's it going to do? It's going to deviate because there's metal and ferrous objects in that panel. And where you mount that compass in the panel will cause different amounts of deviation. So once you mount a compass in an airplane, you have to then figure out, all right, how much is it deviating from north? You find that out. I'll show you how we do it. It's actually pretty simple. And you fill out what's called a compass deviation card, and you mount that card right by the compass. Okay? And with a compass deviation card, it's divided into 30-degree increments. So north, or 360 degrees, then 30 degrees, then 60, then east, or 90 degrees, then 120, then 150, then south, or 180, then 210, all the way back to north. So every 30 degrees, you have some information, you have some deviation information. Once you figure out, when we're doing your planning, once you have come up with your magnetic heading, let's say your magnetic heading is 310 degrees, okay, 310 degree magnetic heading. You're going to find the closest thing to 310 degrees, which would be 300. You look below it and you say, okay, well, they're adding 3, so you'd take and you'd make it 313 degrees. You'd add 3 degrees. You'd add 3 degrees of deviation to your magnetic heading to account for the compass deviating inside the cockpit. Does that make sense? All right. What if you wanted to remount, you got this compass deviation card in your airplane, and you want to take your compass, I don't want it over here, I want it over here. You have to re-swing the compass and figure out how much does it deviate when I move it over here. And here's how we do it. It's really pretty simple. We take, if you haven't seen these, you're likely to somewhere along your flying career. You'll see airports that have these compass roses painted on the tarmac, painted on the ramp at some airports. Just big giant compass rose painted on the ramp. So it'll have a pointing north, east, south, west, and then every 30 degrees in between, you'll have points, 30-degree points coming out of this compass rose. And what you do is you take your plane over to the compass rose, and you park your plane on the compass rose pointed north, and you read the compass. And however far it is, if I was doing this and it read north, I'd put a 0 right there. Then I'd swing the compass 30 degrees, and I'd read the compass. I know I'm lined up magnetically 30 degrees because they have surveyors come out and paint this on there. And I read the compass, and it says 27, so I write 27. And I swing it another 30 degrees, and I write it down. I write down what I see. So that's called swinging the compass. So when you put a new compass in, or you put different radios in that could cause different deviation interference, you got to re-swing the compass. And that's how you do it. You go out and you align the airplane to a known 360 degrees, read the compass, write it down. Swing at 30, read the compass, write it down. Swing at 30, read the compass, write it down. And you fill this out. That's a compass deviation card. Okay. All right, once we've done that, now we have a compass heading. Now we have something we can steer. So it doesn't matter what we drew on our chart, the line, the true course that we drew on our chart. Let's say it was 090. We want to fly directly east from a true course standpoint. Well, winds and variation and compass deviation could mean that we have to have a compass heading of 070. It could be something completely different than 090, but we have to go through all of this process to come up with what do I want to have on my compass while I'm flying so I actually stand a chance of getting where I want to go. That's this process. All right. The next column is the distance column. This is pretty simple. You're going to measure from the center of the airport symbol where you're departing to the center of the airport symbol where your destination is. And you're going to take your plotter and you're going to see, well, how far is it? All right. The key thing you want to be careful of here is use the same units, right? that plotter you have has 2 units on it. One says statute miles, and one says nautical miles. And one's apples, and one's oranges. So if you're using apples, use apples. If you're using oranges, use oranges, but don't use them both. Don't use them interchangeably because they're 2 different units. So whatever you use, so be careful about that. Okay? Yeah, all right, that's pretty simple. And as we're filling this out, I'll show you how we do it. All right, then we have your ground speed column. And your ground speed column, when we calculated the wind correction angle back here, remember we got this information, we just simply put it over here. So this comes from the back side of the E6B when we did the wind correction angle. All right, then we have our timing columns. Estimated time en route, actual time en route, estimated actual, estimated time of arrival, actual time of arrival. Okay, those 4 columns. I generally do not use, you can use them if you want, but I generally do not use estimated time of arrival and actual time of arrival. And I'll explain why when we get to that stage. I use these 2, and then I'll use these 2 boxes for another purpose, which I'll show you. Okay, but these 2 we use. Estimated time en route, actual time en route. And then the last column is the gallons, fuel column. And let me say that the reason we do this whole thing, the reason we go through this exercise is so we don't run out of gas. That's the purpose for the whole thing. If I have 3.5 hours of fuel on board the airplane before the engine quits, I want to make sure I can get from where I'm going, from where I'm taking off to where I go before I run out of gas. The only way I can do that is to do some type of cross-country flight planning and be able to have a good idea of how long it's going to take me. And the only way I can do that is by doing dead reckoning. And the only way I can do dead reckoning is coming back here and having this information to start with so I can calculate everything else. So really, we're doing this to get to here so we don't run out of gas. All right? In reality, sometimes we forget about that because when we're training, we're doing our cross-country flights, how far? 50 miles, 55, 60 miles, just enough to meet the requirements, okay? And we have 4 hours of fuel on board. When it's full, we got 4 hours of fuel on board the airplane, which means daytime. In the daytime, we need to be able to get to our destination and have how much fuel left over? 30 minutes. So we have 3.5 hours of fuel. We're going 50 miles. How long is that going to take us? 30 minutes. Do we really need to do one of these? No. I could use pilotage, right? But we do these because we don't always go 50 miles. What if you're going 500 miles? Well, you have to have a fuel stop somewhere in between. Well, you better plan this thing out so you don't run out of gas, okay? That's the reason we do all of this. Okay. All right. You want to go to Pleasanton or you want to go to Yoakum? Let's go to Pleasanton. All right. Get your charts out. You're on the right side now. And find New Braunfels. Okay? And find Pleasanton, which is just south of, almost straight south of San Antonio. If you follow the longitude line down, the 30-minute longitude line down, it's just south of 29 degrees latitude. And since you're using charts that get used in this class a lot, there may already be a line drawn on there from New Braunfels to Pleasanton. There may already be a line there. If there's not a line there, use a pencil and your plotter and draw a line from the center of New Braunfels Airport, a straight line in pencil, right down to the center of Pleasanton. If there's not already a line there, there's probably already a line there. If there is, just locate the line. If there's not, draw a line. And if you have a new plotter like this that you're borrowing from me, you have to take the paper off the back or you won't be able to see what you're doing. Just peel the paper off the back of that. And if you borrowed a plotter, and I don't know how many I gave out. If you borrowed a plotter and an E6B, I need it back. Unless you want to purchase it, I need it back. Okay? All right, so we're going to plan a flight from New Braunfels to Pleasanton. This is a typical cross country that we do here. We do this one. This is a pretty typical one that we'll do that you'll probably do at some point. All right, everybody have the line drawn or see the line? Okay. Pencil? Yep. There you go.
Thank you.
Mm-hmm. All right, let me go to this one now so I can toggle back and forth. All right. All right, so I'm going to be jumping back and forth between this and the sectional chart because I'm going to be writing information down here. So get your sectional chart and let's talk about, or get your nav log and let's talk about how we fill this thing out. We've gone through the columns. Let's talk about how we fill it out. Unfortunately, it's just about virtually impossible to start on this column and work your way that way. You can't. You're going to be bouncing around a little bit. All right. The other thing that you'll find is that as you plan across country, you're generally not going to plan it the morning of the flight. Generally not. You're going to think about this a few days ahead of time, right? I would hope anyway. Well, guess what? You can't get a few days ahead of time. You can't get this information. And everything is predicated on that information. But you can get some information, right? So what I'm going to do first in one color is I'm going to go through and we're going to fill out everything you could do a week ahead of time, a month ahead of time, right? And then we'll come with a different color and we'll fill in with a different color those things that you do maybe the morning of once you have this information. You calculate the rest of it. Does that make sense? Okay. So the first thing we want to do is we got our line on there. We want to, the way I typically do it is I draw my line first. I got to know where I'm starting and where I'm ending. Got to have that information. And now I figure out, well, what's my true course? So what's the number of degrees? So here's the globe, right? That's north-south. Let's say we're right in the middle of the state here in Texas somewhere. We're kind of going that way, right? Our course line's kind of like that. So we want to know how many degrees is it from here to there. Go. So you're going to use, I'll let you guys fumble with it a little bit. You're going to use this. Remember these from 5th grade math class? Remember those things for measuring degrees? All right. Well, we're going to use this to figure out how many degrees is it. How many degrees is it? And remember, here's a line of longitude right there. Here's another line of longitude right here. So essentially what we're trying to figure out is how many degrees is it? Let me just draw a parallel line of longitude right through here. Okay. We're finding out how many degrees is it from here all the way around to there. That's what we're trying to find out. You're going to use the plotter here, or the compass side of the plot. That's called a compass, isn't it? Protractor. Protractor side. We're going to use the protractor side of this to figure out how many degrees is it from one of these lines of longitude all the way around to there. See if you can figure that out. And I'm going to give you a hint. I'm going to just give you a hint right off the bat. Okay. First of all, it's more than 90, and it's more than 180, and it's less than 270. Okay? It's something like that. So see what you can do, and then I'll show you how to use that protractor to do it here. And then we'll take a break.
Or we could do it this way. We would put the dot on the center. All the way around. From here. And there.
And if you have a plotter like this, then you better get it right. Because this is like a cheater plotter. Oh, you have one like that. There you go.
Yes.
Okay.
Now we know.
Better get it right. All right, let me show you real quick what we're going to do. What you're going to do is you're going to take your plotter, take the top side, take the top side, not the bottom, but the top side that is parallel with the grommet right there. See the little hole? All right, you want to line that up. Line that up on your course line. Doesn't matter where. Line that up on your course line somewhere, but you want to get it at a point where you can put the grommet on a line of longitude. All right, so in this case, you're probably going to have to slide this little past your, well, maybe not, right to where you can get it right on a line of longitude and on the line there. See that, kind of like that? All right, then your line of longitude is going to come up and you're going to go through some numbers up here. What are those numbers that you see? It's not exactly 210, is it? It's a little less than 210. So what is it? What are the numbers? You see, actually, you see two numbers there that make sense, or that could make sense. Or, well, there's only one that makes sense, but what do you see?
Can I get a pencil?
Pencil, yeah.
Pretty much like you said. Maybe. Exactly. Maybe a little to the top.
No, it's fine. Originally I was
Everybody getting it?
reading.
Got 207.
207, 208.
It's so hard to see that line.
What's the other number that it passes through?
20, 28.
27, 28. So if we were going the other way, it'd be 27 degrees. We're going this way, it's 208. 208, 207. So if you came up with 206, 207, 208, even 205 maybe, you're good. Does that make sense? And you came up with it with that? Okay, good.
That would just extrapolate more the further you're going. So if you're off by more degrees and you're going farther,
You'd be farther off, yes. And I'm going to show you in a minute, hopefully by the time we're done here, you'll understand why. If you were to write down, we're going to all put down the same thing for purposes of this class, but if you were to write down here on your true course 205, or if you were to write down 210, I'm going to show you how in the end, when the rubber meets the road and we're actually flying and we get punched in the face with the tactics, we're going to figure out what it really needs to be. This is planning. We have to start with something close, and then we fine tune it. I call it Kentucky windage. You ever heard of Kentucky windage? Right? What's that?
is it a shooting term?
It's like a shooting term, yeah. Right. We're gonna aim there, but we gotta adjust a little bit. And as we're moving along, we're gonna say, okay, well, I need to adjust this way a little bit, and I need to adjust this way a little bit, and I need to adjust this way a little bit. We're gonna do that as we fly. Okay. All right. So let's use 208. Let's just all use the same thing. 208. So right here, your true course, put 208. That's our true course. All right, and let's take a break. We'll get going again. So we got our true course up there. And where do we go from here? What can we do now? We got our true course. We could start working on our checkpoints. Why don't we do that? So let's look at the chart. We already have our line drawn. Let's go to the chart. And let's start thinking about checkpoints and distances. Well, let's first get our total distance. So let's measure from the center of the airport, from the center of our departure to the center of our destination. And how many miles is that? Now remember, let's think about units. We're using statute miles, or we're using nautical miles. I'm going to give you some advice. Use nautical miles. These Remos aircraft, the airspeed indicator is in statute miles per hour, okay? All right, but everything else that we're going to do here in aviation, when you get your winds, they're given to you in knots, right? Most everything we do in aviation is in nautical. So let's use nautical. And then we'll have to make one conversion, but only one, if we use nautical miles. So let's measure it in nautical miles. How many nautical miles is it from the center of the airport symbol to the center of the airport symbol in nautical miles. You have two scales on your plotter. Make sure you're using the nautical mile scale, not the statute mile scale.
Yeah.
53? 53, I don't know, I heard a 53,
It's 51.
51.5, 51.5. Make sure you're going from center to center.
Center, I got 53.
You got 53? No, you got 51.5. 53 would be way over here.
Oh, okay. Oh, that's right. That's.
Make sure you're reading
My
it
eyes are-
correctly. You guys may be reading it wrong. It is 51.5. Okay. All right, so 51.5. All right, so do we want to use 51 or 52? Let's just use this. Let's all use the same thing. What do you want to use? 51?
Round up, 0.5.
52?
Yeah.
All right, let's use 52. Okay. All right. So total distance. So on your chart.
Get there sooner.
Yeah, okay, here you go. All right, so right here in your distance column, all right, so you've got distance, leg, and remaining. So here's distance, leg, remaining. So right here, distance is 52. Put it right there. 52. So everything we're doing right now, you could do anytime. You don't have to, you could do this well ahead of the flight. All right, now let's take that total 52 and let's figure out some checkpoints. All right. So let me say that. Let me show you something here real quick. When we take off, let's say we're taking off here and we're going 52 miles over to here, okay? All right, so we're gonna take off and we're gonna climb to some distance, to some altitude. We're gonna fly and then we're gonna descend, okay? Generally, usually, and we're not going to do this right now because it would be very confusing, but I'll explain it to you afterwards if I have enough time. Generally, this first between here and here, we would say we're departing KBAS. You could actually write this in there right now. We're leaving from KBAS. That's the airport we're leaving from. Okay. Our first checkpoint, our first fix would be our top of climb. So usually, in a practical example, don't write this down because I'm not going to do it for this training thing, but typically the next one would be TOC. So this first line between KBAS and TOC, everything we would put here would have to do with this leg from here to there. Okay? We have to do some more difficult calculations to get there. So I don't want to do that right now because it would be too confusing. So what we're going to assume right now is that when we take off, we're already flying at cruise speed. This would be a slower leg, right? Because we're in a climb. Then we would speed up, okay? So for purposes of this class only, this first line, we're going to calculate, we take off and bam, we're immediately flying at cruise speed, okay? All right. Just wanted to clarify that. All right, go to your chart. And let's look along the chart here. And let's find, from here out, let's find a checkpoint. All right, how far should we go for a checkpoint? We didn't talk about distances. How far apart should checkpoints be? Who said that? 10 to 15 minutes or miles? Minutes, okay, 10 to 15 minutes. What does that mean in miles? So you could use your, yep, you could use that. "10 minutes, let's make an assumption. How fast do you assume you're going to be flying? Ground speed. How fast do you assume you're going to be flying? We don't know, right? Because we haven't checked the weather yet. We don't know what the winds are going to be. But could we make an assumption and be close to say we may be probably flying at 100? Let's just make an assumption that it's 100. So if we're flying at 100, okay, and you go for 10 minutes, how many miles would that be? Remember how to do that? If we know the rate, We point the 60 at the rate of 100. So point the 60 at 100. Were you here last week? Oh,
That's fine.
okay. Point your 60 at 100. Okay? All right, that's our rate. We're flying at a rate of 100. Now on the B scale, last week's class is on our YouTube channel. You could watch it there, okay? Because this is going to be confusing for you, but if you watch that, it'll help. Okay, so we're pointing. So on the A scale, the outer ring 100, the B scale 60 pointed at that. Now on the B scale, find 10 minutes, and look above it on the A scale, and what do you see? Between 16 and 17? So about maybe 16 miles? Okay, so if we go about 16 miles or so, 15 miles or so, let's say 15 or so miles. That's a good distance for checkpoints. Okay, so take your plotter and figure out and come out 15, 16 miles and see if there's anything out there, wherever that is, that what might make a good, easily identifiable checkpoint.
Are we talking miles per hour or knots?
We're talking knot. Oh, you weren't in here. Knots. Everything is nautical miles. We're doing everything in nautical here. Nothing is statute. Do everything in nautical. If you do it in statute, you just have to make sure everything is in statute. All right? But we're going to do it in nautical and make sure everything is in nautical. So if you come out 15 or so nautical miles, where does it get you?
Just about to mid-lake.
Where?
I got near the closer of those.
Should be somewhere out in here.
Yeah.
Yeah.
Okay. So is there anything in this area that might make a good checkpoint? Look at your chart there.
The 2 private airports.
The 2 private airports right here? Okay, all right. What is it about those private airports? What is it about these 2 airports or that airport that's different than this airport? What is it about this one that's different than that one?
That one's public and the 2 ones.
Forget the fact that they're public. What is it about the symbol? Why is that a solid circle and that's an open circle? Paved. This is paved, this is not. If you're not familiar with those airports, you'll never see them. So be very careful about using unpaved airports as checkpoints. You're likely not going to see it unless you know the airport. All right? So I would hesitate to use that as a checkpoint.
You could use Randolph Air Force Base out your right window.
You could use Randolph Air Force Base out your right window, but where do you start your timer? How do you know where you are exactly? Randolph Air Force Base would make a good what type of checkpoint? Positional, situational checkpoint, but not a timing checkpoint. All right? What about right here? You see a road and you see a railroad track parallel with each other right there. Okay? The question though now is where am I crossing it? But that would make a good checkpoint. I'll show you. So take your pencil and put a little hash mark right there across your line, right there where your course line crosses the road and railroad track, the parallel road and railroad track there.
Easier to see.
What's that?
We should have a red pencil, easier to see.
All right. So there's a number of ways that we could verify that we're crossing the road at that point. You have some power lines. Power lines generally, now I didn't talk about power lines. Do power lines make good checkpoints? Can you see power lines?
Yeah, the ground below is clear now.
That's what you'll see. You may not see the power line, but you will see a cleared path where the power line is going. So you actually can pick up power line paths, right? So you could see where this is based on the fact that you have essentially a couple of power lines. You've got a power line going here and you've got a power line going there. So you've got a crossing of, you've got parallel road and railroad track and a power line path right at that spot. So that would make a pretty good checkpoint. All right. What's the distance from the center of the airport to that checkpoint in nautical miles? Nine and a half. Everybody agree with that? 9. Let's make it 9. Because remember, it's not We're not splitting that hairs. All right, so the leg, so the total distance is 52. That particular leg is 9. What's remaining? How much is left in the flight? 43. So when we get to this checkpoint, we'll have 43 more nautical miles to go. What are we going to call this checkpoint? The name, whatever you name, it doesn't matter what you name it. You're the only one that has to recognize what it means. All right. So maybe call it road, railroad track, road / railroad, whatever you want to call it. Just so you know what it means. Okay. So that railroad track on the ground is right here along our flight, and it's 9 miles. 9 nautical miles, or actually NM. 9 nautical miles. Okay. And for the purpose of this class, as we get over here to our ground speed and stuff, we're going to assume that we take off and we're immediately doing cruise speed, even though in reality we wouldn't. Okay, but I'll explain at the end how we account for that. All right. So what we're saying is from here to here. From here to here, this is the line we're working on right here. It's 9 miles. We've got 43 miles left to go. All right. So now go from that checkpoint. Let's find another checkpoint that's 15-ish miles or so away. Okay. So come out from there another 15. It doesn't have to be exactly 15. It could be a little farther than that. Just find what along this route makes sense as a potential next checkpoint. The lake.
The lake, mid-lake?
Yeah. How about that little, now I said lakes don't make good checkpoints typically, right? Because where do you start your timing? But look at the shape of this lake. That's a perfect spot right there to start your timing. And it's also a great situational checkpoint. So right there, the tip of the lake, I would make that a checkpoint. Absolutely. That's a great one. Again, if you're using it, one of my charts, that might already be marked on there because we've done this before. 16? Okay, so go back to your nav log. And this particular leg, now to the next checkpoint, is 16. What do you want to call that? I'd call it tip of lake. Whatever you want to call it, I don't care. Tip of lake. It's 16 miles. 43 minus 16 is what?
27.
So we got 27 miles left to go. Okay. So now if you take your plotter, is there 27 miles left between that checkpoint and the airport? If there's not, we did some math wrong. We measured something wrong.
I got 30.
If you come up with 30, we did something wrong.
Mm-hmm.
So is there 27 miles left between here and here?
Yeah. Just about. Yeah.
Is it 27 miles? Okay, all right. Do we want another checkpoint between here and here? 27 is a long, pretty good distance, right? So how about right here? How about where this highway and this road cross right here? That's a great one right there. It's a great point right there.
Is that 37?
That's 37 and some other intersecting road right there. That makes a great checkpoint. What road is that, Bill? You probably know. You know what road that is? Goes between Floresville and wherever, and whatever. Yeah, it's okay. The point is you'll see it.
Something 81 out there.
Okay, that's all right. All right, so what's the distance from the tip of the lake to here?
Seventeen and a half.
I got 17.
Yes, we got
17?
17 and a half.
Okay. Want to use 17 or 18? Try not to use these halves. It's just, it's ridiculous. Pick one. 18? Okay. 18. What's left over? 27 minus 18 is what? How many? 9 miles? Okay. All right. If you put your plotter down, is it 9 miles from that checkpoint to the destination airport?
Yeah, just about.
If it is, then we've done everything right. Okay. All right. So 9 miles. I'd call that Highway 37 and road. that particular checkpoint. Okay? And then your last checkpoint is going to be your destination airport, which is what? KPEZ? KPEZ, and that's 9 miles, which leaves a remaining distance of 0. So we have 3 checkpoints from departure to destination. So we have this one 9 miles, then our next one is 16 miles, then our next one is 18 miles, and our next one is, this isn't obviously to scale, 9 miles, right? So that's our route right there along the ground. Okay. We could do all of this ahead of time. What else can we do ahead of time? Well, we know we could figure out what is our calibrated airspeed. We could put this in. We can't do our true airspeed because we need this information, but we can put that in. So what is our calibrated airspeed? So let's use our airplanes that we all fly. We're going to be flying at cruise speed, right? We're going to be flying at cruise. So that means, are we going to be flying? Are we flying from New Braunfels to Pleasanton like this? Or are we flying like this? We're flying at cruise, right? So when we look at our airspeed indicator when we're flying at cruise, what kind of airspeed are we getting of those 4 airspeeds? When we look at our airspeed indicator, what kind of airspeed are we getting? Indicated airspeed. All right. What's the difference between indicated airspeed and calibrated airspeed? When we're flying like this. That's the difference. Or it's so close to that that we say it's the same. Why do we say it's the same? Who remembers? Why is indicated and calibrated airspeed essentially the same thing when we're in cruise flight? Why? Who remembers? Huh?
The aircraft is pretty much.
Here's the pitot tube. When I'm flying like this, picture the airflow going in that pitot tube. Picture that airflow. When I'm flying like this, picture that airflow going in the pitot tube. Which one's getting better positional? How is the pitot tube positioned in such a way that it gets better airflow or more accurate airflow, like this? When I'm flying like this, there's a calibration factor I have to apply to what's indicated to come up with calibrated airspeed. When I'm flying like this, they're the same. They're not exactly the same. There could be a knot or 2 difference. But they're so close. They're so close, remember, that when we're talking about general aviation airplanes, like these, and we're in cruise, and our pitot tube is pointed into the airflow, indicated and calibrated airspeed are the same thing. So when I'm flying like this, and I look at my indicated airspeed, that is showing me also my calibrated airspeed. Okay, so when this first line is doing a top of climb, guess what I have to apply? A calibration factor to it, because it's not the same. But once I get here, it's going to be basically the same thing. So in our planes, when we're flying at cruise, in other words, 5,000 RPM, what's the airspeed indicator indicate? Approximately 110. Okay, that's miles per hour. So can we put 110 up here? No, because we're using knots. So we have to convert that. So what is 110 miles per hour in knots? We can convert it right here, remember? So right over here, when you look at this, when you look over at on the A scale, on the outer scale, look at the number 65 and the number approximately 76. You see a couple of arrows there? See those arrows there? One says nautical, one says statute. All right. Under the statute arrow, put 110. Let's put 110 under the statute arrow, and what do you read under the nautical arrow? If you put 110, you have statute and nautical. Under the statute arrow, we put 100 and 100, that's 100, 110. Under statute, we have nautical of 95. 95. So our nautical miles per hour calibrated / indicated is going to be 95. If you wanted to use 110 here, then every one of these need to be in statute miles. If you use nautical here and statute here, everything is wrong. You have to keep all apples to apples or oranges to oranges. You can't mix units. Okay, so we got that in there. Can we get anything else? Can we do anything else here? Yeah, we can do one other thing. What else could we put on here that's not on here yet? Is there anything in here that we could put down? What do you think? Variation. Good. We could put variation. We could put this in. What's our variation going to be? Because that's not going to change between now and next week. Look for your line of variation. Look for your magenta dashed line on your chart, which is near your course line. Find the one closest to your course line. And which line of variation is that? What is it?
4 degrees east.
4 degrees east. So what do we do with east? East is least. So this is going to be a -4. So our variation is going to be a -4. And it says here, minus east plus west. So east is least, west is best. So -4. And that's it. That's all we could do until we have this information right here. Once we have that information, we could calculate, we could figure out what altitude we want to go at. Plus we need to know ceilings on that day. And then we could calculate true airspeed. And with true airspeed, now we can get wind correction angle. We can do all the rest of it. But this is all we can do until we get close enough to the flight where we can get wind direction, velocity, and temperatures at different altitudes to calculate the rest of it. Okay, does that make sense? All right, so now let's say we get close enough to the flight, the day of the flight, and we check weather. Let's do it. Somebody just look on somebody got ForeFlight? Anybody got ForeFlight?
I do, but my app is not with us today.
Your app's not with you? Okay. Well, let's just make something up. Let's say that we check ForeFlight. Let's say there's no ceiling, there's nothing that's blocking us from an altitude standpoint as far as ceilings go. All we need to look at is temperatures and direction and velocity. And let's say that we want to choose an altitude. Well, first of all, we're going to be above 3,000 feet AGL. So what altitudes are applicable that we could use going in that direction? Throw out some altitudes that could work. Remember the VFR cruising altitudes.
Say 4,500.
4,500, 6,500, 8,500, 10,500, 12,500, 14,500. Those are the altitudes we could use, even plus 500, because we're going in a westerly direction. Okay, it's more southwest, but it's a westerly direction. Okay, so all things being equal, would we be better from a true airspeed standpoint? Think about the performance class, and last week we talked about it a little bit. Would we be better if we took wind out of it, just strictly true airspeed? Are we better at 4,500 or 8,500 or 12,500 or 14,500? Which one would be more advantageous from a true airspeed standpoint? Higher or lower? Higher. Why? Faster. Why? Thinner air. Thinner air. Higher we go, the thinner the air, the faster our true airspeed is going to be, right? Well, we have to also now look at the winds. I mean, yeah, well, first of all, let's think practically. We're going 50 miles. Am I going to climb to 14,500 feet to go 50 miles? Of course not, right? But if I'm really going some long distance, maybe I want to get a little bit higher, okay? 14.5 may not be the thing because not going to have oxygen up there. But maybe 8,500. That's a legitimate altitude for one of these planes to do a cross country. All right. So let's say we go to 8,500 feet. All right. Altitude, 8,500 feet. We arrive at that altitude that we want to fly at. Maybe the winds are most favorable up there. We get up to 8,500 feet, and let's say the direction of the wind is 330 at, I I don't know, 15. And let's say that the temperature up there is 10 degrees Celsius. We would get this information from 800WX Brief or 4Flight, or there's lots of different places you could get it. It's all coming from the weather service. But let's say we check that weather there, and this is what we get. So we have a direction of 330. Oh, I'm going to do this in a different color. Do this in green. We have a direction of that's not very visible. Let's do it in red. 330, a velocity of 15 and a temperature of 10 degrees Celsius. Now once we have this information, now we can do the rest of the flight plan, of the planning here. Okay, we have everything we need now to calculate our true airspeed. How do we calculate true airspeed? True airspeed is what? True airspeed is our calibrated airspeed corrected for what?
Wind direction velocity.
Nope. Nope. True airspeed. What two things change in the atmosphere? Those are the two things we have to correct for. What two things change?
Pressure.
Pressure and temperature. So now we have it. We have pressure. That's the altitude we want to fly at. That's not our pressure altitude, but that's the altitude we want to fly at. And we have temperature. Okay. How could we get pressure altitude from this? What is pressure altitude at 8,500 feet going to be? What do we have to do? We could climb up to 8,500 feet and then set our altimeter to what? 2992, but we're planning this on the ground. We're not at 8,500 feet, so what do we have to do? We have to do that math calculation. Remember the calculation? The calculation is 2992 minus what? The current altimeter setting. So what's the altimeter setting here right now? Now somebody go to ATIS and tell me what it is right here, right now. We're gonna calculate this. You'll use the altimeter setting where you're at, which is a sea level altimeter setting. So what is it? You looking for it? 30.18. 30.18. Okay. Well, you got your calculator. 2992 minus 30.18 is what? Negative 0.26 times 1,000. Why are we multiplying it times 1,000? Because the pressure changes 1 inch per 1,000 feet. So 0.26 times 1,000, move that 3 decimal places, this is going to be 260 feet. Negative, that's my negative symbol, negative 260 feet. Okay, we're going to add that to our altitude of 8,500 feet. Which is what? So if we subtract 260 feet off of that, we're going to end up with basically 8,250 or 8,240. That's our pressure altitude. Everybody see that? So when we're planning, if we want to calculate our pressure altitude in order to get our true airspeed, we have to know what the surface, what the sea level pressure is to calculate this. So if we want to get, if we're using the electronic E6B, well, then we could do this. We could come up with 8,240 in this case. Okay. Who remembers doing this calculation using these little tiny numbers in the window here last week? How close can we get to 8,240 using this? Probably not very close. So remember, all of this is predicated on this being accurate. And is this accurate? No. So let's just use 8,500 feet. Unless the pressure is so far off of standard here, I mean way off of standard, then when you calculate your true airspeed using 8,240, does anyone have an electronic E6B? No, okay. Well, if you did, if you calculated your true airspeed based on 8240 versus 8500, you might come up with a knot or two difference. It's not going to matter. It's just not going to matter. So we're not sending somebody to the moon here, okay? So let's not make this crazy difficult, all right? So we're going to use 8,500 feet as our pressure altitude, and we're going to use 10 degrees Celsius as our temperature. We're going to adjust this for these two numbers to come up with a true airspeed. All right, so if you recall, if you set your computer to neutral so that all the numbers line up, set your computer to neutral so that all your numbers on your A and your B scale line up. Over here in this window over here, this bottom window, and not the density altitude window, but the bottom window, you've got two sets of numbers. You've got temperature and you've got pressure. What I want you to do is rotate this so that your temperature of 10 degrees is above, it's positive 10, is above 8,500 feet. Each little tick mark there is thousands of feet as far as pressure goes. So put your 10 degrees opposite 8,500 feet. When you do that, if you have it set up correctly, then your little 60 index is going to be over there close to the 70, pointed close to 70. Okay? So right here, you have, this is 5,000, 6,000, there's 8,500 to be over here. 10 degrees Celsius, opposite 8,500, right there. Okay. Was anybody else not here last week that didn't go through this? Okay. All right, when you have it set up like that, you have 8,500 opposite 10 degrees Celsius. Let me reset mine here. 10 degrees opposite 8,500. Okay. Now you want to find on your B scale, in other words, the middle set of numbers, find the 95. Find your calibrated airspeed, 95 on the B scale, and look above it. And what do you have? Above 95, what do you see?
105.
105. No. You don't see 105. You see 105 above 90. What do you see above 10? What do you see above 95? 110.
Yeah.
110. True airspeed's 110. That's how fast we're going at that altitude with that temperature. Did everyone see that? Do you want me to put the E6B up on the board and show it to you, or did everyone get it? Okay. All right, so now we have our true airspeed. Now we have what we need to calculate our wind correction angle, because we have our true airspeed, we have our winds, and we have our true course. So now we're going to turn our E6B over to the wind side. All right, make sure you're using a pencil for this. And on the wind side, I don't have another pencil, so, oh yeah, I do. On the wind side, the first thing we're going to do, what's the first direction it tells us to do right there? Set wind direction under the true index. What's the wind direction? 330. So put 330 under the true index. Okay? Now we're going to measure the velocity of the wind from this center grommet. So from the center grommet, just put that grommet on top of a whole number somewhere, like 70 or 80. Don't put it in the middle. Just slide it anywhere under a whole number. Just easier this way. And come up 15 units. Come up 15 units and put a little X or a dot or something at 15 units straight up on that little card. Okay? So what you've just done is we've just put our wind vector. Our wind vector is 15 units out of 330. That's our wind vector. All right, what's the next thing say? Set the true course under the true index. What's our true course? 208. So now spin this till 208 is under the true index, and you'll see your X moves. When you have 208 set under the true index, your X should be behind and to the right of the grommet. That shows you where the wind is coming from based on your heading, your true course heading. Everybody there? Okay. Now what's the next thing? Watch that YouTube. Watch the YouTube on this. Okay. We did 3 hours of this last week, so it's, yeah. Okay. Now what's the next thing? What are we doing next?
Slide the wind velocity to the true airspeed.
Okay, so what's our true airspeed? 110. So now we want our, not the grommet, we want the X that we just made, or the dot we just made. We want that to be on top of, right over the top of, the 110 airspeed arc. So slide your card so that the 110 arc is underneath your X. So the X is here, the 110 arc is right on top of it. And when we do that, we get two pieces of information. We get our wind correction angle and we get our ground speed. So what does our ground speed work out to?
Around 118.
So I have my X right here.
117, 118.
Yep. Everybody see that? About let's call it 118. About 118. So our ground speed is about 118. That's what we're calculating. Okay? So our true airspeed is 110, but we have a tailwind component because of where the wind's coming from. So we're moving over the ground. We're estimating that our ground speed is going to be about 118. If these are the actual wind conditions and everything works out, our ground speed would be 118. Now, what's our wind correction angle?
That'd be about around 4 degrees.
Yeah, 3 degrees maybe. Let's call it 3 degrees. And is it 3 degrees to the right or to the left? To the right. So what are we going to do with it? We're going to add it. Plus 3. Plus 3. So 308 plus 3 is, or excuse me, 208 plus 3 is 211. Minus 4 is what? 207? So now we've come to our magnetic heading. Now we would have to go out to the airplane and look at the compass deviation card on the airplane that we're going to be flying to figure out how much deviation we need to account for. Let's just make it 0 so we can get through this class. So let's say it's 0 on that direction. That means our compass heading is 207. So here's what we've done. We've started out saying, so it's not far off. We started out saying, hey, our true course is 208. Because of the winds, we got to add 3 to that. Because of the magnetic variation, we take 4 away. That brings us to 207. So our compass heading and our true course, in this case, pretty much the same thing. It could be way different. Could be way different. Just so happens that it worked out to be pretty close to the same thing. Okay. Everybody with me so far? Okay. Now we're ready to calculate our times. Estimated times en route. We have what we need. I have a ground speed rate of 118. This is how fast I'm going over the ground. So if I wanted to calculate how far is it going to take me to go 9 miles, I can't use this. I can't use that. I have to use this. I got to know how fast am I traveling over the ground. I don't care what my airspeed indicator means nothing when it comes to this. My true airspeed means nothing when it comes to it. What matters is how fast am I moving over the ground. I got to get to that. Now I have that and I have that. How long? Estimated time en route. How long will it take me to go 9 miles if I'm traveling at a rate, remember that? A rate of 118. I know my rate. Point your rate index. Point the 60 at 118. Point the 60 at 118. And go 9 miles. And what number comes up? What's the number you came up with?
17.8.
No. Oh wait, I'm sorry. 9 miles. Yes, I'm sorry. I looked at the wrong. No, 9 miles. Not 9 minutes. 9 miles. You're looking at 9 minutes. Miles is on the A scale. Find 9 on the A scale and look at the minutes scale below it. How many minutes is that? 46. The number that you see is 46. The number is 46. All right, now you got to put the decimal point in the right place. Is it going to take us 46 minutes to go 9 miles? 4.6 minutes. Okay. Now don't spin anything because we're pointed at 118. Now find 16 miles. It's going to be about double that, right? Find 16 miles. How long is it going to take to go 16 miles? 81. So is that 81 minutes? 8.1 minutes. 18 miles.
About
9.2 minutes?
Yeah.
9 miles. We did 9 miles already. 4.6. There you go. There's our estimated times en route. Okay? All right, now, let's look at this total. These total columns down here are important because we're going to use these to cross-check. So first of all, we know that our distance was right because we ended up at 0, so we know our total distance is 52. I could have put this in black, actually, but I'll just do it this way. 52. Let's add these up. Add up, somebody get a calculator, add up 4, 6, 8, 1, 9, 2, and 4, 6.
I have actually a calculator.
$26.5.
26.5. Okay. 26.5. Now, with this still pointed at 118, find 52 miles and see if it should take 26.5 minutes. And if it does, then we've done everything correct. 52 miles should take 26.4. Yeah. Everybody see that? So that cross checks. Okay. We got 5 minutes. Let's do the fuel thing, and then I'll have the last hour to go through this topic line with you. All right, so fuel. Now we're going to do fuel, the fuel side of things. How much fuel are we going to burn? Well, we have to start out by knowing how many gallons per hour we're burning. We got another rate of fuel burn. Where are we going to get that information from? What?
Pilot operation handbook.
Pilot. I've never heard it called PO. Yeah.
It's-
POH.
You listen to the aeronautical book on.
Oh, yeah, it does. Okay, POH or the airplane flying manual or whatever. We got to get it from the manual, right? So we have to know what power setting are we flying at because the fuel burn rate is going to be based on the power setting. The lower the power setting, the lower the fuel burn. But we're going to be flying at 5,000 RPM at cruise power setting, and if you look at the book, that's going to say we're burning about 5.5 gallons per hour. All right? So I want to put 5.5 gallons per hour up here. Oh, that I could have actually done in black also. You could have done that ahead of time. All right, so if I'm burning at a rate of 5.5 gallons per hour, that's my rate. What am I going to point my rate at? What am I going to point my 60, which says rate on it, what am I going to point that at? I'm going to point it at the only number that could represent 5.5, which happens to be 55. So you're going to point that at 55. That's the rate of fuel burn. Okay? So remember that A scale, that outer ring, either represents miles or it represents gallons. It represents that particular unit of measure that we're working on, miles or gallons. The B scale is always minutes. How many minutes are we burning for this first leg? How many minutes are we going to go 9 miles? How many minutes? So find 4.6 minutes on the B scale. Find the only number that could represent 4.6 and look above it. The only number that can represent 4.6, what's the number above it? 42. So, now we got to put the decimal point in the right place. Would we burn 42 gallons of fuel in 9 minutes?
About 0.42.
0.42 gallons. All right, now find the only number on the B scale that could represent 81. Don't spin anything because we're still burning at 5.5. The rate is still 5.5. Find 81 on the minutes scale, the B scale. When you look above 81, what do you see? What's the number? 74. Are we burning 74 gallons?
No.
Are we burning 7.4 gallons? Are we burning 0.71 gallons? Yeah, 0.71 gallons. Now find 9.2 minutes on the B scale. What's the number above it? 84. So we know already that's going to be 0.84 gallons. And then and we already did 4.6 right there, so we know it's going to be 0.42. Okay? Now we're going to do another math check. So add these up. Somebody add these up for me. How many gallons are we burning here? Total. 2.4? Okay, let's call it 2.4. 2.4. All right. Now, leaving this on a fuel burn rate of 55 or 5.5, if you're burning at that rate for 26.5 minutes, how much fuel are you going to burn? 26.5 minutes is going to give me 2.4. See how we cross-check all of that? Okay. Let's take another break. Okay. Let's talk about what we do. We have this figured out. We get in the airplane, and this is our strategy. This was our plan. This is what we plan on happening. But remember, this is only as good as how we calculate it, and it's also really only as good as the accuracy of that information right there. Because everything out here is it's really predicated on that right there. So if this isn't right, the rest of this isn't exactly right. It's going to be really close. I'll tell you that. It's going to be really close. But it's not going to be exactly right. So this is where the pilotage side of things comes in. So you get in the airplane and you take off. And again, I'll show you how to do the top of climb here in a minute. But assuming we take off and we're instantly going cruise speed, which we're not. Okay. But assuming that, then it should take us 4.6 minutes to get to our first checkpoint. All right, well, what if it doesn't? What if we start our timing and we get to our checkpoint, which we can visually see? That's the importance of using the pilotage side of things. We visually see it, we start our timer, we take off, we head that way, we get to our checkpoint, and we stop our timer, and we realize, you know what, it took us 5.0 minutes to get there. So this was our estimated time en route. Our actual time en route was 5 minutes. Well, now we have to do some recalculating while we're flying. We're doing some housekeeping in the airplane. So now, while we're flying, you need to tell yourself, what is my actual ground speed? So go ahead and do that. Calculate that. So we know now we don't know our rate. Now we're trying to find our rate. We know our time and we know our distance, so what is our rate? This we do while we're in the airplane flying. So you're going to use this again, and now we know two things. We know distance, so I'm going to give you a hint here. We know A scale, we know B scale, and 60 will be pointing at our rate. We know A scale, so A scale, B scale, 60 will tell us our rate. So 9 over 5. 9 over 5, 60 points at what? 108. So our actual ground speed is 108. Everybody got that? Everybody see that on here? All right. So now based on that, now I'm going to show you how I use these columns. You can use these columns. Let me explain what these are, first of all. Let me explain what these columns are. So the estimated time en route, actual time en route, you can see what that is. Estimated time of arrival would be something that I never use because I just don't care. would be, let's say that my time off, let's say that I took off at 12 noon. That means that my estimated time of arrival would be 12:05 or 4.6, 12:05 or something like that. And then this one would be add 8.1 to that, and it would be 12 whatever. I don't care. I don't care what time it is on the clock. Is it 3 o'clock in the afternoon or 4? I care how many minutes am I flying from this point to that point to that point. Does that make sense? That's why I don't use this column. I don't use that column. What I use this column for now is this right here in the airplane. If I've calculated that first checkpoint, my ground speed to be 108, now I want to know, all right, well, if I'm only doing 108, what's it really going to take me to do 16? I'm not going to do it in 8.1. What am I going to do it in? If I'm doing 108, it's going to take me what? It's not going to be 8.1. It's going to take longer than that. What is it? My new rate is 108. I'm going 16 miles. Where do we point our rate? It's already there. We just calculate it. If our rate is at 108, if the 60 is at 108, my distance is 16 on the A scale. How many minutes is below 16? 8.9. So instead of 8.1, it's going to take me 8.9. I'll use this column now. That's how I use this. You see what I'm doing here? Okay. So all of these other columns now, these actuals and this side, I use this to really figure out what's really happening. What's really going on while I'm flying. Why do I care? Well, I care because if this flight plan takes me to the edge of my fuel, and I have a planned fuel stop, okay, I ain't going to make it. I'm not going to make it. If I'm flying 10 knots slower, or I might not make it, depending on where that's at. If I have it right to the edge of my fuel, my legal fuel, I won't make it. And I track this trend as I'm going. And if this trend is holding, then I know that I had better start planning right now for another fuel stop before my planned fuel stop. Make sense? Okay. If I'm not doing this as I fly, I likely am going to run out of fuel. Okay? Or the opposite could hold true. What if I did it instead of 4.6, I did it in 4? Well, now I'm going faster. Well, now that means, well, maybe I can go farther. I maybe start looking, well, I can get a little farther. I can take a fuel stop a little farther out. Unless I have, usually for me, it's my bladder that tells me when I have to stop. My bladder can't make it as far as the fuel can usually. But that's the reason for doing this as we go. All right? As far as our heading goes, as far as our compass heading goes, here's what's going to happen. This is where I use this term Kentucky windage. We get out and start flying. We start heading on our way. Here's our first checkpoint right here. We're flying a compass heading of 207. Let's say we get here, we find the roads, but we realize we're over here someplace. We've gone a little east of course, holding 207. Well, what I'm going to do at this point, as soon as I recognize that, is I'm going to turn, get back on course, and then instead of using 207, I'm going to adjust by a degree or two, one direction or the other, to make up for the fact that the wind blew me off. The wind's a little off. It blew me off a little bit. I'm going to hold a new heading, and I'm going to track to my next checkpoint. And as I'm tracking that next checkpoint, if I see I'm not going to make it way ahead of time, I'll start making adjustments. That's my Kentucky windage. I'm making adjustments as I fly to keep myself on that course line. I start with 207 because that's what I calculated. And if I ended up at 208 or 206, I start with 208 or 206. But as I'm flying, I'm looking out the airplane and I'm saying, well, that's not going to work. Let me change it by a degree or two or 5, whatever. I'm making changes as I fly. But the only way I can make those changes is by looking outside the window and looking at my chart and looking out the window and looking at my chart and saying, that's not right. That's not right. Let me make a change. I calculated 207, but that's not working. So let me change it. Okay? All right. That being said, here I see this a lot. I see students take off. And let's say they got 207 calculated. I saw this the other day. I did a stage 3 check with, he's not in here so I can say it. And this is where he was going. And this was his plan. And it was hazy. And he took off and immediately started heading this way, right, like this, right over the top of Randolph Air Force Base. Now he climbed up to 4,500 feet, so he was above it, but he climbed up, by the time he got to 4,500 feet, he was right here, he leveled off, and we're right on top of Randolph Air Force Base, heading towards the Charlie. And I said, where are you at? And so all he did is hold his, I think his calculated, with the winds, his compass heading, I think it was like 212 or something like that. So he held 212 and never looked outside the airplane. He just took off, started climbing, holding 212. That's great. That's exactly what you're supposed to do. But you need to look out the airplane and make sure 212 is working. Okay? So just because you calculate something doesn't mean you just fly that and just say, okay, well, that's it. I'm just going to fly 207 to whatever and not look outside the airplane. You have to look outside the airplane and make sure everything is working. Okay? All right. Now, let me talk about practical versus practical being what you're going to really do versus testing. Okay. For testing, and by that I mean written testing, written test. If you get a written test question where you're calculating something here, you split gnat's hairs and you try to find the exact answer, okay? From a practical standpoint, don't split gnat's hairs. Don't take 8,500 and do the math here to figure out that it's 8,240 for the pressure altitude. If you get this question on the written test, you need to come up with 8,240 for your pressure altitude, or you're going to get the wrong answer. Okay? But practically speaking, just use 8,500. Unless the pressure, 2992 is standard. Well, what if the pressure was, 27? Well, you wouldn't be flying because there's a hurricane, right? But unless the pressure is way off, it's not going to change that much. Remember, it's 1 inch per 1,000 feet. So if this were 2892 or 3092, well, now there's a 1,000-foot difference. Now you want to think about it, right? But this is 0.26. It's 260 feet. It's not going to change things that much. Okay, so just think logically about it. Let's look at fuel. All right, this is pretty accurate. With fuel, from a practical standpoint, always be conservative. Always round up. You could be ultra conservative and say, yeah, the book says 5.5. I'm going to say 6 gallons per hour. That's ultra conservative. You could say, all right, 0.42, let's make it 0.45. Let's make this 0.75. Let's make this 0.9. Let's make that 0.5. Right? Be conservative, whatever. Always be conservative with fuel. Never try and, well, it's going to be, 4.25 gallons. No, let's just make it 5 gallons or 4.5 gallons, right? Be conservative when it comes to fuel.
Basically the same thing with motor.
Yeah, you don't want to run out of fuel.
Crossing Puget Sound.
Let me say, where's Wood? Never run out of fuel in an airplane. There is never, ever, ever, ever a valid excuse for running out of fuel in an airplane. Never. Let me just knock on it everywhere here. Okay? The only time you can tell me that you ran out of fuel and it wasn't your fault is if the gas tank sprang a leak while you were flying, you didn't know it, and it all drained out. That's it. Otherwise, there's no excuse for it. Okay? So be conservative and know your fuel. All right. Does anybody have any questions on what we did here? All right. I'm going to erase all of this, and I'm going to now show you how we do the top of climb using this same thing, okay? And you'll understand why I didn't include it at the beginning, because it can be confusing. I want you to understand the process here in the columns and what we're doing. So I'm going to erase all of this. You don't have to erase yours. You can if you don't want to, but I'm going to move this down to here because this would all apply once I got here, right? Once I got into the cruise, once I got to 8,500 feet, that would be the case. And the winds would be 330 at 15 and 10 degrees. And my trigger speed would be 110 and 208. And that would be 211 and 207 to 207, right? 0 minus 4 plus 3, right? That would hold true once I got to altitude. Okay. But getting to altitude, those numbers wouldn't apply. So let's get rid of this first line right here. Okay. And I'll get rid of all of that. All right. So if we're going to use a top of climb, okay, we don't know what the distance is going to be because we don't know how long it's going to take us to get to altitude. I don't know how long. I don't know the distance because if I've got a strong headwind or if it's a cold day or a hot day, my climb performance is going to be different. So this number, that 9 miles, is going to change. And the time it takes me to go that 9 miles is going to change because my ground speed could be different based on winds and all those factors. So that's the complication with calculating a top of climb. So there's a couple of ways to do it. If you're flying an airplane that has climb performance charts in the pilot operating handbook, you're simply going to go to the climb performance charts and it's going to calculate, or you'll be able to use those charts like we did in the performance class and say, okay, my time to climb is X, my distance downrange is X, and you can then put that information, you have to account for wind, but then you can put that information directly in here. The REMOS doesn't have that. So we have to calculate it from scratch, which is kind of good because you get to learn how to do it, okay? So what do we need to know? Well, I need to know what this is. I can't, and I would do two things here. I would do this. I'm at 95 once I get here, but in the climb, I'm not at 95. I'm not doing 95 in the climb. What do we climb at? What's our VY climb speed? Come on, everybody should know that. What's VY climb speed? What's the speed you climb at?
75.
75, okay. 75. That's miles per hour. What is that in knots?
86.
What's that?
86.
No, it'd be the other way. Be slower.
70.
So if it's 75 miles per hour, how many knots is that? Remember, use the conversion scale on the E6B. So if it's 75 miles per hour, that is, let's call it 65 knots. See that? So 65. And is that going to be my actual calibrated airspeed? No, it's not. I would have to go to a calibration chart. The REMOS doesn't have a calibration chart. So we're just going to use 65 and understand it's not exactly right. But guess what? It's not exactly right. None of this is exactly right, but it's pretty close and it'll work for us, okay? All right, so we have 65 for our calibrated airspeed, but what do we use for here? What do we use for our direction, velocity, and temperature? All right, well, here's what you do. This is why I don't show you this right off the bat. Here's our takeoff. Here's our climb. This is the point we're trying to get to right here, top of climb. Top of climb. And we begin our cruise. All right. What do we know about the wind direction and temperature right here? We know that it is, because we got this from the Weather Service Station, we know that it's 330 at 15 and 10 degrees Celsius, right? What do we know it is at the surface? Because we can get this from ATIS. What is it at the surface? Somebody tell me ATIS, right, what the ATIS information is right now at the surface. Wind direction, velocity, and temperature.
Let's see, 040 12 knots.
040 at 12. And what's the temperature here right now? In Celsius.
Temperature right now in Celsius is 21 degrees.
21 degrees Celsius. Okay, 21 degrees Celsius. All right. We want to go to 8,500 feet. Right? What's the altitude of the airport right here? 650. Let's call it 500 to make this, just so you understand the math here. We'll call it 5. This is at 500 feet. What's the halfway point?
Like 4,000.
4,000 feet. So 4,500 feet MSL or something like that. Would that be right? Whatever it is. Okay. If I just simply, this is a simple way of doing this. Remember, this is not exact, but it's close. If I wanted to interpolate between here, 040 to 330, what's the median? 040 to 330, what would the middle be? That's a big swing. So 040 is over here, 330 is over here. The middle is about 10 degrees or 5 degrees, something like that, about 10 degrees. I'm just looking at a compass rose here. About 10 degrees. So wind's 010. Temperature difference. Velocity, 13 or 14, pick one. 14. Temperature difference. Or what would the temperature, if it was the median, be between 10 and 20? 15? 15. That's what we're going to use. 010, 14 velocity, 10 degrees Celsius. I'm just going to come up with a median. And I'm going to fly, and I'm going to calculate using that median to get my average on this leg right here. Does that make sense? Is it going to be exactly correct? No. Does it need to be exactly correct? No. Why? Because we're going to be looking outside the window as we climb to make sure that it's working properly. That's why. Okay. So using this information, now I can calculate my average true airspeed along that climb. So I have an altitude of 4,500 feet as an average. So my pressure altitude and my temperature, what's my true airspeed? So we're going to put 4,500 opposite 10 degrees Celsius over here in this little box. Go ahead and do that. 4,500 opposite 10 degrees Celsius. Calibrated airspeed speed is 65. True airspeed would be 70 in the climb as an average. Okay. So airspeed of 70, or ground speed, average ground speed of 70 in the climb. Okay. Or true, not ground speed, true airspeed of 70 in the climb. True course is still 208. All right. What's my wind correction angle now? Bill, go ahead and do that real quick since you got it right last time. Wind correction angle, 208, 70. Wind velocity, 010 at 14. Give me the wind correction angle. All right, so the first thing we do is the wind. So the wind is 010 at 14, so put 010 on your true index. Mark up 14. Spin to your true course of 208. Move your wind velocity dot under 70. Okay, what do you got? What's your ground speed? About 82? See that? About 82. So the ground, oops, happened. So the ground speed for this particular leg is 82. All right. So if my ground speed is 82 over the ground, now I need to figure out what is my time to get to 8,500 feet, or essentially to climb 8,000 feet. All right, now, what's my climb rate? What's your typical rate of climb in that airplane when you're flying at VY, full power climb? What's your climb rate? You should know this by experience in flying the airplane as much as you've flown the airplane. What you think your average climb rate will be, you know it's going to change as you go up in altitude, right? What's a fair number to estimate? I've talked about this a lot. What's a good number, what's a good climb rate to use in these airplanes, especially climbing to an 8,000 foot altitude? Huh? 500 feet per minute. So 500 feet per minute, okay, 500 feet per minute for how many feet? 8,000 feet. How long is that going to take? Climbing 8,000 feet at 500 feet per minute, how long is that going to take?
4 minutes?
No, you went the wrong way. Other way. 16 minutes. 16 minutes. So my time is going to be 16 minutes. So if I know that I'm traveling at 82 miles per hour over the ground for 16 minutes, how far am I going to go? And that tells me where this point is. So what's the answer? I'm going 82. My rate is 82. Point your rate at 82. My rate's 82. My distance is 16. Or excuse me, my time. My time is 16. My time is 16. How far did I go downrange? What's this distance right here? 22 miles. 22 nautical miles. So now I know my top of climb. I can go to my chart and I can simply measure 22 nautical miles, and wherever that is, boom, there's TOC. So my cruise starts from there. Does that make sense? In theory, the way we did it. I mean, I know you got to practice and do it a few times, but that's the concept of how you get your top. You have to back into your top of climb. You got to back into your top of climb. Okay. You see why I didn't teach that right off the bat? It's a little bit confusing. Okay. Now let me say this about top of climb. If you're flying across country and you're going to, let's say, 4,500 feet. Now I'm talking practical. Do you need to calculate the top of climb? Does it really matter that much? Doesn't really matter that much, right? Your first checkpoint, let's say it's 16 miles out. You know you're going to reach top of climb before you get there, but you calculated it as though you took off and started doing cruise right away. What's going to be different is when you reach that first checkpoint, your timing is going to be off because your ground speed wasn't what you calculated. Okay, so what? It's off. But from there on, it should be correct. And I know that it's going to take me longer to get to that first checkpoint because part of it was climbing to get to altitude, and then I started cruising. So mentally I know that, and I don't care that much. If I'm going up to 8,500 feet or 12,000 feet or something, now maybe I do want to calculate a top of climb because I'm going from a fuel burn standpoint. My fuel burn's different. When I'm climbing, am I burning 5.5 gallons per hour? Burning like 7.5 gallons per hour. Full power. Cruise is not full power. Cruise, we're bringing that power back a little bit so we're not burning as much. So, excuse me. So if we have an extended climb, excuse me, we need to calculate, or it's better off from a practical standpoint, to calculate a top of climb. Something in my throat. To calculate a top of climb for fuel burn purposes and to get your timing more correct. But if you're not going that high, don't worry too much about a top of climb. But you need to understand how to calculate and how to get there. Okay. Any questions on that? All right. I'm going to let you guys calculate a top of climb real quick. I'm going to give you some information and let you guys do it. Actually, I shouldn't erase that bottom one. Tell me again what the conditions are here at the surface. I shouldn't have erased it. 040 wind. 040 at 12. And what was the 21?
Yeah.
21C. So that's conditions at the surface. Are you looking at foreflight? Somebody go up to 9,000 feet and give me the winds give me the conditions at 9,000 feet. Let's use an actual example here. You got it?
249.
At how much? 8. And what's the temperature? 7. Okay, so here's your condition at the surface at this airport. Here's our current or our forecast or current conditions right now that they're forecasting for 9,000 feet. So what would you use for your top of climb information right here? What would you use and what altitude would it be at? So we're going to assume that 65. So I already calculated that means 70 from a true airspeed standpoint. So we want to know what's going here. So that's this. What would you put right here? And what would you put here for altitude to calculate this on? You're gonna find the median. Find the median between this and this. What's the median between that and that? The median between that and that? The median between that and that? That's what's going here.
Is the altitude where this airport is at 0 or 500?
It's actually 650 feet, but if you use 500 feet, it's an easier one to work with because it's close to 500, right? All right, so you could assume this is 500 feet. Who's got some answers?
I know what the altitude.
What's the altitude?
4250.
4250. Okay. Anybody got a wind direction?
Sort of around 130.
320. 040 249. Yeah, that sounds like it'd be about right. 320, is that what you said? Okay, 320. Okay.
14 degrees Celsius.
14. No, wouldn't be 14, it'd be 10. Be between these two.
I was thinking.
Oh, wait a minute. I'm sorry. I'm looking at the velocity. The velocity between these two would be 10. Temperature would be, temperature would be 14. Yeah. Sorry, I was looking at the wrong thing.
That's okay.
14 degrees C. All right. So now you have what you need. Now you have what you need to calculate. Actually, not true airspeed. Now you have what you need to calculate true airspeed. So we have 320 at 10, and we have 14C. Okay, so what would the true airspeed be? What would the true airspeed be? And we said the altitude was 4250 is our median altitude we're working at. So if you can find 4250 on here, then more power to you. 4250 at 10, right about there. 65. Yeah, still about 70. Still about 70. Okay. All right, keep going. Get your wing, get your ground speed. Get your ground speed so we can calculate how far downrange we're going, and we can calculate the time and all that kind of stuff. We would ultimately want to figure out what is this distance right here. What's that distance? And then we want to figure out how much time, or excuse me, we want to figure out what the time is to get to that altitude so that we can back into the distance. Okay, so you're using the back side of your triangle, or your back side of your E6B. First thing you want to do is the wind, your wind vector. So you've got 320 at 10. So set this up with 320 at the true index. Put 320 at the top at the true index. Mark a pencil mark 10 units up. Just 320 at 10. Turn this to your true course of, oh, I didn't put that up there, 208. That didn't change. 208 is our true course. Spin it to 208. Then slide this until your dot is over the top of 70.
That's 72.
And what did you end up with a ground speed?
That's 72.
72. 73. Anybody come up with anything way different than that? All right, let's use 72. So our ground speed is 72, so the wind's not really giving us too much of an effect here. We may have a wind correction angle, but the speed is not changing much. All right. So if we're doing 72, that's our ground speed. All right, that's the speed that we're traveling over the ground as we're in this climb, or that's our calculated speed that we're traveling in the climb. Okay. Now we're going to use, for our purposes in these planes, an average climb rate of about 500 feet per minute, because that's what these planes will actually do. When you first take off here, what's your climb rate? It's closer to 1,000. They got a good climb rate. But the higher we go, remember the performance class, the higher we go, the less efficiency we get out of that engine, the lower that climb rate gets. And so we end up with maybe an average of around 500 feet, or that's a good average to work with anyway. So we're traveling, we have to climb how far? From here to here. What's our climb distance in feet?
About 8,400 feet.
8,500 feet, okay. And if we're climbing at 500 feet per minute, how many minutes is that going to take?
Let's see.
16.5? 17?
That's 17.
Okay, 17 minutes. 17 minutes at 72 mile, at a rate of 72 for 17 minutes, how far? Rate of 72, you know the rate. Remember, if you know the rate, just point at the rate. So point the 60 at the rate, 72. Now we know the minutes, or excuse me, yeah, we know the minutes, 17 minutes. And you look above 17, 22. About the same as what we just did, isn't it? 22. So 22 miles downrange. So if we started at 52, we know we got 30 left before we reach top of climb. Everybody see how you do the top of climb? Okay. If you're flying an airplane that has time, speed, distance to climb, you just look at the chart. If you're not, or if you don't think that's correct, which it may not be correct based on maybe it's an old aircraft or the engine's worn out, it just doesn't do that, you can calculate it manually like this. All right, this is not absolutely correct. It's close. It's close. All right. Maybe you get there in 17 minutes, maybe it takes you 18, maybe it takes you 16, whatever, but it's close, right? You have some idea of what's going on. And then from that point, now from top of climb to your next checkpoint, would be the cruise numbers that we did before, and it would maintain those. Now, what about your descent? On the descent side, we get over here where we're going, and we begin our descent. Do we need to change anything there? Do we need another line for our descent? Typically, I don't, and I'll tell you why I don't. It will change a little bit, but what I'll typically do in the cruise as I get to my point of descent, and let's say I want to descend at 500 feet per minute, because that's a nice descent rate as well. If I need to descend 8,500 feet, or maybe the airport I'm flying to is a different elevation, but I know how many feet I need to descend. Let's say I got to descend 8,500 feet, and I'm descending at 500 feet per minute. When do I need to start my descent? 17 minutes before I get there. So 17 minutes before I get there, I'm simply going to pull the power back a little bit. I'm going to pull it back until I see I have the power set to where I'm descending at 500 feet per minute. Did I change my speed? No. I didn't change this one. This one will change as I descend. This gets slower and slower and slower as I descend. My true airspeed gets slower because I'm getting into thicker air. But it's not throwing me that far off going 8,000, in that distance. So I simply will keep my numbers the same. I'll get 17 minutes out. I'll pull the power back until I see a rate of descent of 500 feet. I'll just leave it right there. I'll leave it trimmed for cruise. Pull the power back. Boom! I just start descending right into my destination. That makes sense? So the descent isn't so different. It isn't so different from a speed standpoint like this is. This is way different. This is way slower than my cruise, but my descent is not.
And that gives you a safety factor too on fuel, because you know you're...
I know I'm pulling power back. Exactly right. It's exactly right. But I don't change my fuel calculation at all. I leave it where it's at from a conservative standpoint. Okay? In theory, we covered a lot today. So if this is the first, how many of you, this is the first time you went through a navigation class? It's a lot, isn't it?
Yeah.
There's a lot. There's a lot here, okay? So I know that much of it, and especially if you didn't do the E6B class, a lot of it probably just went straight over the top. Don't worry about that, okay? And I'll tell you why. First of all, you're new enough in the program where you're going to go through this class with me again. Not only that, when you get to your cross-country phase with your instructor in the actual flight training, you're going to do a dozen of these. You're just going to be doing a lot of these. You're going to get practice at doing these, okay? So what I hope for is that if you haven't gone through this class before, at least you understand theory behind what we're doing and maybe some of the process behind what we're doing and why we're doing it. That's the important thing, and then you can build on that, okay? All right, any questions? I got done actually 10 minutes early. I'm proud of myself.
The average wind, how did you...
The average wind, you just average it. So if the wind was 12 here, velocity, you talking about the velocity or the direction?
Correct.
So 040 to 250. So I didn't do it, I just took the word of somebody here. But if you take what I would do when they're that big a difference is I'll just look at the back of this and I'll find 250. 250 here and 040 over here. And I'll kind of put them about in the same place and look above. And I find the midpoint of about I find about 330, but 320 is pretty close, yeah. You see what I did there? I just put 250 here and 40 there and look right what's in the middle.
Okay, yeah, I missed that.
Yeah. Because they were way different, so yeah. And you have to be careful about something here when you're finding these medians. The difference between 40 and 250, that's a big difference, right? So it could be that when you really be careful with this, because if you take off at 320, you want to eventually go 250, but if you take off on a heading of 320, really be looking outside that window and making sure, hey, this isn't going to work at all. I need to be adjusting this as I climb. Okay? In no case should you just stare at a heading and think, that's it. I'm not going to cross-check this with anything. Don't ever do that. All right? Okay. Next week is Thanksgiving, so we're not going to have class. The week after that,
Pretty sure the week after is federal.
federal aviation regulations. So, get lots of sleep because you will fall asleep in class if you haven't got a good night's sleep while I'm trying to teach FARs. But it's as boring as it sounds, and it is boring, it's very important, okay, to come to this class. What I'm not going to teach you in this class is the federal aviation regulation. That is not what I'm going to teach you. Here's what I'm going to teach you. What I'm going to teach you, I don't have a book here. What I'm going to teach you is what is the book? It's a reference book. How do you use it as a reference book? How do you find things in it? How do you look things up? What parts of the FARs are you more likely to use for the type of piloting that we do? So basically, how do you navigate through the book? We're not going to be talking about, you'll get some regulations out of it just simply because we're talking about it. But my goal is not to say, here's the regulations and you need to know these regulations. That's not my goal. My goal is to say, here's how you find what it is you're trying to find in this book. Okay? So that's why it's important to come to this class. Happy Thanksgiving.